All right, so we're continuing where we left off yesterday. We're going over graphs of exponential and logarithmic functions. So remember back to Algebra 2 when you learned what the graph of a logarithm was. It's the reflection of your exponential over the line y equals x. Reflecting over the line y equals x creates an inverse function. So the inputs of our exponential graph are the outputs of our logarithm. The outputs of our exponential graph are the inputs to our logarithm. And so where an exponential is approaching 0 on the x-axis, and then it increases rapidly to infinity. In the case of its reflection, now it's approaching the y-axis. So it's approaching 0 on the y-axis. Now it has a vertical asymptote. So our exponential has a horizontal asymptote of y equals 0, and our inverse has a vertical asymptote represented by x equals 0. And then it does increase forever, but it increases very slowly. All right, it's increasing very, very slowly. All right. Now, one of the key points, so the key things to recognize is a vertical asymptote of 0 and that the input of 1 gets a 0. Those are really key points to recognize. So characteristics of logarithmic functions, the characteristics. The domain is all positive real numbers. Notice it does not include 0. It cannot reach 0, so we use a open parenthesis. So that's my domain. Its range is all real numbers. So the domain and range is flipped from what an exponential has. All right. Key point is that all logarithms that don't have a shift, all logarithms of the form log base b of x, all go through 1, 0. They all go through this point. So they all have an x-intercept of 1 and no y-intercept. If your b is greater than 1, if your base is greater than 1, the graph goes up to the right and is increasing. If your b value is between 0 and 1, the graph goes down to the right and is a decreasing function. All right, so if your base is bigger than 1, you increase, and basically it's a reflection. It ends up reflecting over your y-axis is what's going to happen when that base is between 0 and 1. All right, so the graph of f of x equals log base b of x approaches but never touches the y-axis. Never touches. All right, so it's a vertical asymptote. All right, so all of our translations are the same as every function you've learned. If you have a value on the outside of your function, it's affecting your output, so it shifts you up and down. So it creates a shift up C or down C. If you have a value inside your logarithm, it does the opposite of what it looks like. So normally it's x minus h in there. So if it's x minus a number, then I'm going to the right that amount. If it's x plus a number, I go to the left. If it's a negative in front, that's a reflection about the x-axis. If it's a negative inside, a reflection about the y-axis. A constant multiplied in front creates a vertical stretch. If it's bigger than 1, it creates a, they say shrink or a compression if it's between 0 and 1. And if it's inside that 1 over b value, then if it's greater than 1, it's a compression. If it's between 0 and 1, it stretches. So let's find the domain of this logarithm. Well, we know the normal domain is 0 to infinity. So log base 4 of x would have a domain of 0 to infinity. So let's figure out where this graph went. So normally that's x minus h. So in this case, my h value is 3. That means my graph went, my h is negative 3. So that means my graph went left 3. Since it went left 3, my domain shifts left 3. So my domain is now from negative 3 to infinity. So it's based upon that value inside the logarithm. So go ahead and try this one. Hit pause. When you're ready, hit play. All right, so to check our answers, this time that x minus h form matches. So that means my h is 5. And so it went right 5. Since it went right 5, my domain is now positive 5 to infinity. Notice I'm still not including that endpoint because that's my vertical asymptote. That's my vertical asymptote. I can't actually reach it. All right, so some basic properties of logarithms. Log base b of 1 is 0. Log base b of b of 1. Log base b of b is x. So these are just all the properties we did earlier in the notes all put together. All right, and now natural logarithm, all the same properties apply, except natural logarithm, your natural logarithm is a logarithm of base e. A logarithm of base e we represent as ln, the natural logarithm. So that means that a matching base is e. So that means when you see e inside of ln, the base matches. If you see any other number, the base doesn't match. All right, so finding the domain is very similar here. So on the first one, I have a couple things happen. My x is now negative. So that's really negative. That's really negative x minus 3. It's really negative x minus 3. All right, so that means it's reflected. So rather than going from 0 to infinity, now it's going to have a negative infinity to 0 situation. It's going to have a negative infinity to 0 situation. And so that means I'm going to start at negative infinity and go until something. And that's because the x is negative. Since the x is negative, it reflects. All right, now what would make the inside of the parentheses 0? Your domain always ends at whatever value makes it inside of your parentheses 0. And so 3 makes it inside of that parentheses 0. So there's my domain. All right, so on the next one, this time we also have a square. So if I go ahead and put this one in, it's not changing my asymptote. Why is that showing up? Half right 3. So all it's doing to the domain, the domain is starting at 3 and going to infinity. It's still starting at 3 and going to infinity. The square does not affect the domain. It does affect the shape, but it doesn't change the domain. So you should be hitting play because you're checking your answers. So my domain switches on this one, so it starts at negative infinity, and then what makes inside of my parentheses 0 is 4. On this one, the square doesn't affect my domain, and there's no shift, so it's just all positive real numbers. So 0 to infinity. All right, so how can I use this to solve? When the outside air temperature is from 72 to 96 Fahrenheit, the temperature in an enclosed vehicle climbs by 43 degrees in the first hour. The bar graph shows the temperature increase through the hour. The function of f of x equals 13.4 ln of x minus 11.6. All right, and so then we want to part of this question is missing. 1 second while I find the remainder of the question. All right, so the remainder of the question is use a function to find the temperature increase to the nearest degree after 50 minutes. So we're figuring out after 50 minutes. All right, how well does a function model the increase shown in 3.16? All right, so let's figure out what f of 50 is. All right, so you're going to want to grab a calculator here. You're going to want to grab a calculator, or you can use Desmos. Desmos can calculate this for you. So 13.4 natural log of 50 minus 11.6. And so I'm getting 40.821 degrees. So let's see. There we go. That matches. That matches. Yeah, it's not exact, but it's pretty darn close. It's pretty darn close. All right. So this function is used by scientists to model, in this case, the temperature increase in a closed vehicle. So after 50 minutes, the temperature can increase by 41 degrees in an enclosed vehicle. That means if it's 100 degrees outside already and you close that door to the vehicle, it can be 141 degrees inside that vehicle after 50 minutes. Okay, so not the kind of place you want to leave your pets or any kind of human being. All right, so go ahead and try the next one. Hit play when you're ready to check your answer for 30 minutes. Okay, so you should be hitting play to check your answer. And so when I put in 30 this time, 30, I get 33.976. And so if you compare to your table, this one is actually even more accurate. It's closer to that 34 degrees. So there we go. And that's it for the notes for today.